All right, so I'm going to be talking to you today about our approach to using deep learning in a lot of different Google products, and TensorFlow, which is the system that we've built and recently open sourced to make this kind of machine learning approach easier. And this is in collaboration with a lot of people at Google, so this is not just solely my work. There's a lot of people involved in this work. So I think one of the things that's happened over, say, the last decade or maybe a little bit more is that we've now got a pretty good handle on how to store and then perform computations on large data sets. So things like MapReduce and Bigtable that we've built at Google, things like Spark and Hadoop, really give you the tools that you need to manipulate and store data. But honestly, what we really want is not just a bunch of bits on disk that we can process, but we really want to be able to understand this data. We want to be able to take the data that our products or systems can generate and then build interesting levels of understanding. So what do I mean by understanding? So if you take this photo, any of you, I could say, could you tell me what's in that photo? And you could actually compose a coherent sentence that describes, you might say it's a cute little girl, she's got a teddy bear, that kind of thing. That's the kind of thing we would really like our machines to be able to do. And similarly, if you take a street scene like this, there's a lot of text there. You'd like to be able to read all that text, understand it, understand where it is. So for example, we could send you to that men's suit store if you're nearby and need a suit, even though the text is obscured and it's on the second floor. There's a lot of understanding you can get from being able to look at the real world through perceptual data and really understand it. Similarly, if I'm speaking to you, you'd like to be able to have the machine understand what it is that I'm saying in the same way that you're able to hopefully understand what I'm saying. So neural networks are this incredibly powerful abstraction that can do a lot of these things. They can learn a really complicated function from data. And by function, I don't mean y equals x squared. I mean something very different, like you take in raw pixels and you can output a word that is what is in that image. So these systems work because they're very powerful and they build these layers of abstraction automatically in the course of trying to learn to accomplish this task, which is to learn this function that you're trying to train them to do. And they're loosely based on what we know about the real brain. I say loosely because we're not simulating things at the low level of neurotransmitters or chemical interactions, but we have high-level abstractions of things that behave in vaguely similar ways to real neurons behave. So each neuron is typically connected to a bunch of neurons. They tend to form in these layers in these models so that higher layers can build interesting combinations of lower level features that have been detected. The neuron sees that input and decides, is that interesting to me? And they learn to cooperate. So we have a lot of these neurons in these machine learning models, and they learn to cooperate to accomplish a complicated task, like telling you what's in an image given the pixels. So the functions are typically simple. They're typically like a little matrix multiplier, a little vector dot product, plus a bias through some small nonlinear function. But the composition of millions or billions of neurons is actually quite powerful. So that's deep learning in a nutshell. Here's a very sort of cartoonish representation. If we're trying to train a model to tell us from the raw pixels, is that a cat or a dog? It will take in the pixels. Some of those neurons in that first layer will activate based on what they see, the second layer and so on, propagating up through the model, and we'll say, that's a cat. And we'll say, oh, actually, that's wrong. And so through the process of training the model, we'll make little adjustments to all the neurons that fired to say, no, you should believe this is more dog-like. And we can actually determine throughout the whole model what adjustments we want to make it more likely that the next time we see data like that we'll say dog instead of cat. That's training in a nutshell. It's a very computationally intensive process. These models have lots and lots of floating point operations involved in them, but ultimately they can do pretty powerful things. And a really nice property that neural nets have is the results tend to get better if you train them on more data and use a bigger model, and that generally requires more computation. But if you do that, you can get really amazing results. Obviously, better training algorithms and new insights and so on really help, but the ability to scale actually is at the core of making these things work incredibly well. So when we started this project in 2012, there wasn't much use of deep neural nets at Google. And we started collaborating with our speech team as kind of one of the first production deployments. And then we started collaborating with some image and perceptual teams. And over time, what we saw is that we built tools that other teams could pick up and use to solve their problems. And that the tools that we built were actually incredibly general purpose. A similar machine learning model in one area would be able to be almost completely repurposed with maybe very minor modifications in a completely different domain, a different kind of area, just by training it on slightly different kinds of data. And I'll show you some examples of that. And it's very broad. So you see the kinds of applications that these systems can solve or work or help with. And it's everything from robotics and photos and images and natural language understanding. It's very, very nice. So TensorFlow is a system that we've built that allows us to express machine learning ideas and then train them and use them and deploy them in real products at scale. And we released this as an open source project in November 2015. And it has a really nice Apache 2.0 license, which sort of means pick it up and do whatever you want with it. And the code is available on the web. And it's had pretty good, strong external adoption. So this is kind of a graph showing GitHub stars and forks, which is at least some semblance of how much the community is interacting with these different projects. Cafe, Torch, and Theano are three other open source deep learning frameworks that have been around for a little while. One of the things that's interesting is there's a lot of demand for trying to do this kind of machine learning and making it easy with tools like TensorFlow. People really respond well to that. So, for example, TensorFlow had the most forks of any GitHub repository in 2015, and we became available in November. So that was kind of surprising to us, but very pleasing. And the motivations for us to build this project were that we built an earlier system that we did not open source that was scalable and really good for production deployment, but it wasn't as flexible as we wanted for research purposes. You couldn't express every kind of machine learning system. If what you wanted fit well in the kind of APIs that it provided, that was great, but if what you wanted was a little bit different, it was actually quite hard to express new kinds of machine learning models of certain classes. And so we really rebuilt that system and built TensorFlow with the idea that we wanted to keep the scalability and production deployment aspects of the first system, but make it much more flexible. And better understanding of the kinds of things that people were using this kind of approach for allowed us to really simplify it in a lot of ways. And so we're hoping that TensorFlow becomes one of the standard ways in which you can express machine learning ideas and computations. And we think it's actually quite useful in the context of other open source projects. For example, we often internally will use a MapReduce pipeline to prepare input data, and then we'll use TensorFlow to train a model, and then we have a system that can push those models out to serving that we've also open sourced called TensorFlow Serving. So all these pieces can work together to really make something that allows you to solve problems that you really care about. Okay, so we have a website. I think one of the things that has worked well about the TensorFlow release is that we put together a lot of tutorials about how you can use TensorFlow in different ways, walking through both the machine learning aspects of it and also how you actually do this particular thing in TensorFlow. So we have examples of a lot of the kinds of models that I'll describe in the TensorFlow website, and I think that's been one of the keys to people adopting it. Okay, so what is TensorFlow actually? So at the core, it's this graph execution engine, and I'll show you in a minute how we get some of those graphs. And it's designed so that you can run these graphs on a variety of different kinds of devices and seamlessly move from something where maybe you're training a model in a data center using GPUs, and then you want to be able to run the same model in an app on your phone, and you want to be able to take that model and move it seamlessly between those different environments. We have different front ends for specifying and driving the computation. Mostly people use Python today. There's also C++ front end. There's more that are in the works. That's actually one of the things that the open source community has been contributing is various kinds of front ends for this. There's some pull requests out there now. So you're going to build a graph that for example, computes a neural net inference. So here's a very simple graph. MNIST is kind of the hello world of machine learning. It's a bunch of handwritten digits, and you want to identify, is that a 3 or a 7 or whatever. And so this is kind of the lowest level model. We actually have higher level ways of expressing these kinds of things that are more compact, but I want to show you kind of the gory details of if you really care about getting down at the very low level, you actually have control over exactly what's going on. So this is kind of the API you would use, and you would say, one of the things that TensorFlow has is automatic differentiation. So you can say, here's my model, and now I want to optimize it with respect to this loss function, which might be like, is that a cat or a dog? If I get that wrong, that's a loss function, and then I can automatically, symbolically differentiate the graph and understand what kind of updates I want to make to the whole model in order to make it more likely that I say dog the next time I see that example. And so you say, I'm going to train it with a technique called gradient descent. I'm going to use a gradient descent optimizer, and then I'm going to minimize the cross-entropy loss, which means for a multi-class problem, I'm going to try to minimize the error I make in saying cat instead of dog. And then I'm going to launch the graph and run a bunch of examples through it in a loop. And that's basically the code. I don't want you to understand this in detail, but that's kind of the amount of code you'd write to do a digit classifier. And what results from that is we end up with this graph, which is the basic computational abstraction in TensorFlow. But mostly that's hidden from the users. They're writing code like you saw in the previous few slides. And underneath the covers, we have this computational graph. And the things that flow along the edges in these graphs are tensors, multi-dimensional arrays with various kinds of types. So a 2D array of floating point numbers or a 3D array of integers, those kinds of things. And we've augmented what you think of as the traditional data flow model, which is mostly functional and purely stateless, with state. So the parameters in the model, the things that hold the weights that I associate with all the different features in my model are going to be variables in this graph. And we have operations that can update those variables based on the computations that I'm going to do. So for example, biases here is a tensor that's going to represent a variable, and we're going to have this minus equals operation, which will subtract a little bit of the output of the multiply from the biases and update it. So the other important thing about TensorFlow is we want to map these abstract graphs onto different kinds of computational devices. And so we can automatically take that graph, the underlying system decides, oh, it should run this part of the graph on GPUs, and these parts need to be run on CPUs because maybe those operations aren't supported on GPUs, and automatically does that. It seamlessly inserts these send and receive nodes that manage all the communication underneath the covers that you don't really see as a user of the system. And then that same model, because we can do this placement and decomposition of these graphs, can run on everything from phones to single machines to distributed systems. At Google, we've actually been building custom machine learning hardware. We announced a project called the Tensor Processing Unit, which you see here, this funny board that actually accelerates lots of kinds of machine learning operations. Some external third-party companies have announced sort of more mobile-oriented custom chips. So this Fathom thing here is from a company called Movidius that has a custom ASIC, and you can plug it into a USB port and get sort of high amounts of computation available there. OK, so let me just walk through some of the uses that we've been using for deep learning at Google. So as I said, one of the first things we did was work with our speech team to really improve the quality of our speech recognition models. And through a series of different updates of the model to use sort of more computationally expensive neural nets, we've actually been able to reduce the word error rate very substantially. You know, this is like a huge improvement. And really, it makes the phone a much more usable device when it actually really understands what you're saying, regardless of the noisy conditions or other things. Google Photo Search, using the ability to go from pixels to what's in that photo, actually allows you to search your photos without tags. So for example, you can see, you know, you can search for my photos of Siamese cats, or we can organize all your photos by categories so that, you know, you can click on birthday and get all your birthday photos even though you never tagged them. We just know these are photos of birthdays. You know, a user wrote, wow, it's the new Google photo search is a bit insane, I didn't tag those. It's very important that you be able to retrieve even odd images of Yoda, like macrame Yodas, from your repository of photos. Another example is just like a little small project that we put together that allows you to find rooftops in our satellite imagery, and then estimate the size of the rooftop and the angle, and then can tell you, if you're a homeowner, if you installed solar panels, how big an installation could you have, how much energy would that generate? And this is normally something you'd have a solar installer come out and like consult with you for half an afternoon or whatever, and we can just do this algorithmically from the satellite imagery data. The recent AlphaGo competition, where DeepMind's system played the world champion in Go and defeated him 4-1, which was kind of a big breakthrough, actually used TensorFlow for training some of that system and used the tensor processing unit custom hardware to run the system during the matches. A system called Smart Reply. We actually had an April Fool's joke in 2009 that said, oh, Gmail will now respond to your email automatically. And it turns out we actually launched a real product around this in 2015. And in 2016, more than 10% of mobile inbox replies are sent via this feature. So just to give you an example of how this works, you get an incoming email. You can't read the text, but it says, we wanted to join you to invite you to Thanksgiving on November 22nd. Please bring your favorite dish RSVP by next week. This is an email my teammate received from his brother. So we have a small neural net that says, is a small response useful for this kind of message? If yes, then we activate a more computationally expensive model, and we predict some replies you might want to give to that message. Count us in, we'll be there, or sorry, we won't be able to make it. And the user can just click on them, they can edit the reply if they want, and so 10% of replies are now sent. So really understanding is pretty helpful. Here's an example that combines computer vision and translation. So this is actually all running on the device. So there's an OCR model that's trying to detect text and then find it and translate it into your native language. And the user's native language is kind of switching for the purposes of this video. And you can see that you hold it up to a sign and you get it in your native language. Works for restaurant menus, that kind of thing. And that's all on device. Image captions research. So I showed you that image earlier. This is actually an image that the model was not trained on, but as a test image. This is 2 different outputs from a model that can caption images. And it can actually generate a whole sentence about an image, just given the pixels. And the model says, a close-up of a child holding a stuffed animal, or another sentence from the generative model of sentences is, a baby is asleep next to a teddy bear, which are pretty good, right? Like a human actually annotated this, a young girl asleep on the sofa cuddling a stuffed bear. If you'd asked me, several years ago, could computers write sentences about images? I would have said, I don't think so, at least not for a while. But they can actually do that today. There's some other examples. It's not 2 pizzas, it's actually 3, but on 2 pans. And if you squint just right, I assure you there is a man flying through the air while riding a snowboard. You can't see the snowboard. So one of the things we actually focus a lot on is turnaround time for experiments. So being able to take a model and have an idea about a machine learning model that you want to try for this particular problem and turning that around in like an hour or a few hours is a very different kind of research than if your experiments take multiple weeks or multiple months. If it's months, you're like, oh, why did I start this experiment in the first place? I've forgotten by now. And so we actually focus a lot on that. And one of the ways we do that is with parallelism and lots of sort of computational resources applied to the problem of training the model in parallel. And so you can see, we use data centers like that. And one of the things that really helps, you can use a GPU card to train these models. And this shows the accuracy in the y-axis and hours of training on the x-axis. And with 1 GPU card, it takes a while. If you throw 10 GPU cards at the problem, it's much better, and 50 GPU cards is significantly better. So it's not quite linear speed up, but you get about a 30x speed up with 50 GPU cards in terms of time to accuracy, which is what you really care about. OK, so how can you get started with machine learning? So there's 4 ways with varying complexity. One of the ways is using cloud-based APIs where you don't actually do the machine learning. You let other people do the machine learning, like us. And then you can use these APIs in your system. The second is you can run your own pre-trained model where we have trained the model and you just run it on your machines, but you're not actually doing the machine learning yourself. And then the third is use an existing approach that has worked well in another domain and train it on your data so it works well for your problem. And then the fourth is developing your own completely customized machine learning models. And obviously, as you go down, it's more flexible, but more effort is required. So cloud-based APIs, Google has a whole suite of these. Other cloud providers often have these. We think ours are better. And so I'll just show you the Cloud Vision API, where you give us an image, and we give you back good stuff about the image. And so, for example, here's an image. You give us that image. We tell you that's running in a marathon. You give us the image on the right, and we find faces in it. We tell you that they're happy, and we tell you we found some text, and here it is, and it's in Spanish. And you can actually, get the ASCII values of the words, or men's suits from that earlier example I showed you. We also have a pre-trained model, which allows you to essentially do the same kinds of things at least for the image classification on your own devices. So you can download the parameters of a trained model, run that model, and use it. So for training your own models, there's two choices. One is you can run the open source release of TensorFlow, for example, on your own physical machines or on virtual machines, sort of low-level cloud VMs in a cloud hosting environment. We're also working on a cloud machine learning product, which is in alpha, that allows you to, at a higher level, say, I just want to train this model. Please make it go fast and train it quickly. And we're going to try to make that as seamless as we can. We have about 15 to 20 customers using the alpha right now, and we're going to take that feedback and bring it to beta as quickly as we can, and then general availability. So for example, you can train a model on your own image data, but reusing the model structure. And for this, you don't really have to be a machine learning expert. You can use the TensorFlow tutorials and essentially just download that model, point it at your data that is labeled with image pixels, and then this is a picture of golfing or whatever. Or you can develop your own. OK, I have one more example. One of the things that's going to really change in the world is now that computer vision really works, it's going to really impact a lot of things. So this is a lab we set up with about 20 robotic arms. And one of the things we've done is we've just trained them to pick things up. So they're learning on their own from a model driven by the camera pixels. The cameras are in the upper left above the shoulder there. To torque motor controls. So there's no control system in here. It's all completely learned. And it's just learning to pick things up on its own. And over time, the model gets better and better because you can tell, is that a successful grasp or a failed grasp by whether the gripper completely closes or partially closes and has successfully retrieved an object. And so that's, robots are always fun. That's an example of the kind of thing that I think will have a big impact. So next slide, please. Thank you. And in conclusion, these models are actually making a really big difference. And if you're not considering how to use them in your product, you probably should be. And I have one more slide with some URLs in it. So thank you.